Okay.
It's cool sitting on the beach. Saw the tide come in. There was that sandbar that I walked across, and then like about 20 minutes later, it was almost under. Try to get a crab. I found that its hole, and I saw it pop out quickly, and I tried to dig it out. I try to like coax him out by like covering the entrance. Like I figured like at some point he's gonna have to come out. He waited me out. He won.
He probably has like an underground tunnel system.
No, I put a stick down there. It ends.
Did you poke it?
I don't know. It was a very flimsy stick, but
Maybe
it did actually. It's kind of cool.
Okay. We'll wait another minute just in case someone connects in time. Did you commit any other form of entertainment rather than running?
I swim
Oh,
and bike. And
in the pool or in the open ocean?
I didn't swim in the ocean yet. I want to. Aaron, Landon, and I tomorrow after your chair session, we're going to go kayak.
Oh, that's great plan. And if anyone is listening to us, they will be jealous.
Oh, trust me, my girlfriend's not too impressed with me right now. It's our 1 year today.
Oh, whatever.
And it also dropped 4 inches of snow back up there.
What are you supposed to do about that, though?
We're down here relaxing on beaches and stuff, and they go through a winter storm.
Perfect.
Okay, well, thanks for for coming and joining it in spite of hard travel. This will run out of batteries quick, so I will try to squeeze. So that we, last, this is standard thing, and we are trying to get through the artifact, and you have heard the Professor Vince Arstitz, who gave a very nice overview from bird's eye. But we need to go into tiny details of Hartree-Fock equation so that there is no reason to go anywhere else before we get this little things. So the concepts are your favorite Slater determinant, and we need the variational theorem, we need Coulomb exchange, and then after we wrap it up into a concept of atomic molecular orbitals going to Slater determinant, we will write down the algorithm how the code is working. We are skipping everything related to nuclear degrees of freedom. We have only electronic degrees of freedom. These three terms in Hamiltonian. The electrons interact with each other, and therefore they take different orbitals. And the goal is to project multi-electron problems onto several one-electron problems. And this is done by making another your favorite equation, average of quantum average of multi-electron over the electron number 2 of it, whereas all but one electrons. And we are going to do it. Then one is getting equations for, like in 2 electrons, equation for first electron and second electron. But right now it is not yet solvable because we do not know how to. We do not have algorithm for solving it. We need something for this interaction terms. And the variational principle tells that if you already know perfect wave function with minimal energy, and then we try to vary it a little bit, the energy will always increase. And this principle is fundamental background for search for self-consistent algorithm to solve Hartree-Fock equations. So this is something we will come back next week. So the atomic orbitals, this chi, looks like X, centered on different ions with different coefficients C, form molecular orbitals, right? And molecular orbitals composed with the Slater determinant make overall big wave function that no one draws. It's multidimensional. It's just a concept, right? Atomic expansion coefficient, molecular orbital, overall wave function. And the variational principle of slightly varying orbitals or wave function until we get the right one is applied by optimizing those C coefficients. So we need equations that will help us to update these coefficients until we are happy with them. It is not for pen and paper, it's for computers, for programmer in the bathtub, same style. And there will be equations very similar to Schrödinger equation with the letter F instead of H for to glorify Fock. So last thing we overviewed before departing from class last time was that if we practice Slater determinant, right, if our wave function is Slater determinant, and we want to practice a way to find total energy, we put operator in between and Bra and Cat on the left and right of the wave function. And due to antisymmetry of Slater determinant, there is an artifact. It is, I was going to collect your signatures for a surprise that everyone believes that electrons repel each other, that electron-electron interaction gives positive contribution to energy because they have the same charge. But due to antisymmetry, there are terms with negative charge. So sort of electron interaction that stabilizes the system. Negative. It is a big surprise. And it is why Hartree-Fock is better than pure Hartree. Okay. So I don't know. I had some comments, but we can go. So it was done. What was done before? What we are doing now? I'm going to show the same two terms that we overviewed. One is I just want you to surprise you. Therefore, I will show it in a second later. And there will be pictures so that you do not feel bored. So there are two types of contributions to Coulomb interaction. One repelling, another attracting. And we do have equations for each of those. But those equations are so boring for everyone that smart people recognize it, find a way to represent equations in form of pictures, and got a Nobel Prize for it. So if you hate equations, do not worry. Nobel Prize holders hate them as well. Okay, so it is most intense slide of today. Those are equations which are boring, and those are pictures that are much better. So here we have the repulsion of two electrons. So it is at site 1 orbital 1, at site 2 orbital 2, and here on the right side also position 1 orbital 1, position 2 electron 2, sign plus. So repel. Now we will look later on the second how we can interpret. Electrons are very rarely sit in some locations. Sometimes, most frequently, they move. And if electron is moving and there are no interactions, it will move on a straight line. Right? But here is an abstraction. If it feels, it is not feeling second electron all the time. It just randomly feels it for just one short interval in time and then forgets about it. So it scatters. One electron scatters from another one. So it goes up, bumps into second electron and goes to different direction. Reasonable. Right? But the second electron also bumps into first one and goes into different directions. So they just come in and out. Very natural. Repulsion. If like two billiard balls collide, they will run into different. So the lines are freely distributed, freely moving electrons, and this wavy line is their bumping. their interaction. Basically, Feynman got Nobel Prize for things like this. Here, everything is natural. We can follow it, right? But how do we interpret the second term, which has negative thing? So we know if we follow equation, position 1 orbital 1, position 2 orbital 2, and after interaction, position 1 orbital 2, position 2 orbital 1. So the electrons swap their badges after interaction. And instead of bumping and going away, they are kind of going through each other. So the number 1 becomes number 2. Number 2 becomes number 1. But it is because of this wavy line which corresponds to Coulomb interaction. So the first one is true Coulomb. We keep the old name Coulomb, and the second one is exchange because they swap the badges. Right? And if you write equations, you just swap indices or positions and put number minus. And if you do these Feynman diagrams, you just make them to cross and go. So, from point of view of theoretical physicists, all universe corresponds of just such interactions, and we just draw diagrams and tell, here is the equation of everything. So, what are we going to do? Right now, we have very strong baggage. We have all components, and we need to slowly go to equations that we will be able to solve. Okay, so we need to one electron equation, which takes into account influence with another electrons, and we need to remember we need a procedure that makes a hybrid operator that is not an operator in the second electron, but still operator for the first electron. So we are going to practice it, and we are going to practice it towards our Feynman diagrams, towards the Coulomb and exchange. Well, forget it. I'll show it next time. This is what I like. So this is same equation as we had before for Coulomb. So, but I am intentionally removing one electron away. Okay, erase last 30 seconds. I need to go to previous slide. So if you want to find total energy, we need to integrate over all electrons, first and second. And so we need to have this Coulomb interaction, and then 4 orbitals, 2 before, 2 after. And we can symbolically do it in this. First we integrate over second electron and call it letter J, and then we multiply it by first electron and integrate it over 1. And at the result we get not an operator but a number. Total contribution from Coulomb energy. Good. I will erase those wrong 30 seconds if I have time. So this is number, but we know operator, we know number, but now we need a hybrid, a thing that is an operator that acts not on 2 electrons but only on the first. So if we scroll back and speak not about the last thing over here, but previous step, J with head. So we perform integration over second electron, and then this construction will be an operator in respect to the first electron. So if you plug it into here, it will be the standard way of finding expectation values. So let's focus on this construction and what is the properties and how can we use it. And if you want to do same construction for exchange, we just swap indices and put minus same. So this Coulomb operator for one electron carries information about distribution of second electron in average way, but it acts only on electron number 1. So operator acts on the wave function on the orbital. So operator here acts on the wave function. We know that this overall Coulomb interaction should be described by this Feynman diagram. But how do we implement into this diagram the integration over position of second electron? Means that integration, instead of having specific lines, we just take all possible positions and all possible velocities, and an average cloud representing second electron will be like a wall from which first electron is scattering. Okay, so it is structureless wall that provides scattering of the first electron away from here. So repulsion means it bumps and scatters away. So this is Coulomb one electron operator for Huxley. And then we can practice the same thing for exchange. See, the indices here are swapped. And now we again will draw a box that represent average cloud of electron number 2, but something crazy and counterintuitive happens. So, like, I'm coming to the mirror, bumping into it, and at the same instant I'm coming out, but my face is changed. So it was electron number 1, it bumps into here, and then it comes out as electron number 2. So they're swapping. We do not need to imagine it. It's crazy. It's better just to follow equations. But if we miss this term, then most of molecules will become unstable. They will self-explode. So this is a reason why molecules are stable, why there is a stabilization factor, why the additional contribution to total energy that is negative. Draw a box and it bumps and changes identity. Focus. And for Coulomb there is a convention to use the letter J, and for exchange the letter K. I disagree with these notations, but it is what is used in literature.
Wait, for Coulomb you use what?
Huh?
What letter do you use for?
For Coulomb, for the standard repulsive thing, it is J, and for the attractive, crazy thing, it is K. Almost done. We will be done in a record short time. Miss our meeting.
You recognize it as what? Nope.
So, if we want to be masters of these notations, I do not want to be one, but just in case, if you want to play with this sort of equations every day, there is a third way. First way, pure equation. Second way is the pure pictures. The second way is abbreviated shorthand notations, because we will have integration variables the same, first and second, but the Coulomb interaction in the denominator doesn't change. We need only the indices of orbitals, and if we have indices of orbitals more than 2, like some Latin alphabet R, S, T, U, we can put it into the just brackets. And some literature, maybe we will not face this literature in our life, but just in case, maybe here in the conference you'll see, and some people believe that everyone accepts this notation from kindergarten. So this round bracket, and vertical line in the middle, it means this 4 orbitals or 2 electron integrals. Okay, this column. And if you have the indices coinciding before, we are finishing very soon. This lecture. Take a seat. So if the indices coincide, like before vertical line the same and after vertical line the same, it will correspond to repulsive coulomb. And if they are different before and after, it will be exchanged. That's it.
Nice to have a very end.
So what we will be doing next time, we will take this positive repulsive coulomb and negative exchange into one electron operator and recast it in the basis of specific orbitals, and then just set up the algorithm how it is solved. Thank you for joining. And the meeting number 13 is done. Anyone online wants to ask questions? Okay, if no one is here, the meeting is dismissed. The meeting is dismissed. Angela, you can stop the equipment. We are going to disconnect.
Okay.
Thank you.
I have none.